Well, I thought I'd start my little presentation on these two sections of Chapter 10, okay? Try and help you understand what this is all about. And the rest of the homework's been posted for the semester. It's all on Blackboard. Did you guys see the instructions for the final project?
You can email it to you or print it out.
Either one. I mean, that's, yeah, because you're going to be doing so much on the computer. If you'd rather just give me computer files, you can do that. But if you want to print out your work, that's fine too. Yeah.
Do you want the work to be what kind of came up on Excel if we used it?
That'd be fine, yeah. That'd be fine. I mean, you know, I'm trying to look, I think there's 4 problems you have to do. I want you to do 4 different types of problems, right? Well, one has to be from Chapter 10, and that's one of the reasons I'm talking about this now, right? One has to be from Chapter 9, and you're kind of free after that, right?
9, so we can do 9, 10, and any other chapter we want.
Sure.
It doesn't have to be 7
No.
or 8 or anything.
No, you could do 12. We'll be doing 12 by the middle of this week. You don't have to. You could pick something else, okay?
So what was the very large one that we had to do?
Again, it's your choice. So, again, I like to teach these 2 sections together. Correlation is the first, right? So what are the basic concepts? You're going to have 2 variables, right? I'll usually use x and y because when you took algebra, that's probably what you did. But a correlation exists between 2 variables when the values of one are somehow associated with the values of the other in some way, right? So if you think about what I was just doing in the problem from the book, right? What are the 2 variables? Well, shoe print and height, right? So, you know, I could do this. I could say, here, I'm going to work on the chapter opener here. In the chapter opener, there's this problem. We could let x represent, well, the shoe print measured in centimeters. And we could let y represent the height in centimeters. And now I want you to understand what we're doing here. There's a claim being made. And it's kind of funny that that's how I'm stating the problem. A claim. Because you guys, I'm doing it because you're used to it now. Right? We made claims in chapter 8. We made claims in chapter 9. What did we make claims about? A lot of different things. What kinds of things did we make claims about? What kind of claim are we making here? I am making a claim that a correlation exists between, well, it's funny, shoe print and height, right? That's my claim in English. Now, I still haven't really explained correlation. A correlation means, you know, there's a relationship between, well, because the shoe print is X and the height is Y, that's what I'm really claiming. There's a relationship between X and Y. Now, it's a claim. Is it true or not? Well, that's what I have to help you to understand. We can use the ideas we've learned in statistics to establish whether or not there's a relationship, And if there is a relationship, then what section 3 about is kind of how do you use it? How do you use the relationship? So, let's take a look. Oh, here's your new statistic for the section 2 tonight. The linear correlation coefficient, R, measures the strength of the linear relationship between the paired quantitative x and y values in a sample. I wouldn't write all that down, but I would write this down. I would say R is my test statistic. Right? Isn't that what you guys usually do? Right after you write down what the claim is. Oh, I guess you need a null hypothesis and an alternative hypothesis, but then what's the next thing you do? You compute the test statistic, which could be what or what so far? Z or T, right? Well, in this type of problem, it's going to be a different test statistic called R. It's called the correlation coefficient. That's too big a print. But here, this says what the other slide said. Sometimes R is a positive number. Sometimes R is a negative number. Now, I guess I'll give you guys some guidelines for R. Okay? It has a complicated formula. I'll show it to you, but you're not going to use the formula to compute it. We're going to use software. Okay? So a couple things about R. Here's an inequality that I can write down. I don't know why I wrote that arrow above it. That's so funny that I did that. It's because I've been teaching Calc 3 all semester also, and they have vectors. Anyways. R is between -1 and 1, always. It can't be any higher than 1. It can't be any lower than -1. Okay? The way it's going to work is this. If there is a linear relationship a positive value of R means a positive slope. Now here's an old idea you guys had back in algebra class, right? What do you guys know about slope from your algebra class? Yeah, that's one thing, right? We used to write M for slope. Do you know what slope is? Rise over run is a nice way to think of it. Right? So a positive value of R is going to mean a positive slope, and a negative value of R means a negative slope. So if you remember what that idea of slope is, and if I take a look at these pictures up here on the screen, okay? I mean, here's the question. That first set of data, is it described by a line? Is there a linear relationship? Now, you have to understand, when I do this, it's very, very rare that you're going to get all the data to line up exactly on a line, right? Actually, that's not going to happen. Even if it's truly modeled by a line, it's not going to exactly, because we're making measurements, right? We're going to have little errors here and there. But this would be a positive slope. Why? Because you rise every time you run. Whereas this, we have a negative value of r. What's the rise over run here? Well, the rise is actually falling when you run. This is a negative slope, right? You might remember, what do you call it when you have a horizontal line? What's the slope?
Zero.
That's 0, right? So it's either a positive slope or a negative slope we can describe, and that's related to r. R is not the slope, but it's related to the slope. And we'll see how, I think, through the formulas in a little bit. How about this one? Well, they say here r is 0. No correlation, right? There's no best fit line that's going to tell you much of anything here. Okay, so you have to keep in mind that sometimes the data we talk about is not linear. And so if the correlation coefficient is near 0, you're not going to have much of a relationship at all. Now here's another situation to worry about. This. Here r is really small. R is very close to 0. It's not exactly 0. And if I tried to do linear regression on this set of data, I'd be in big trouble. Actually, you might know from your algebra. Do you guys know what shape that is? That's a parabola. It's not a line. You want to know what's happening here probably? Here, throw something through the air and watch it. The path that it took is modeled by a parabola, not a line, right? I guess if I threw it through the air, there was no gravity, it would have been a linear relationship. So this one's non-linear. We're only going to deal with linear regression. There are plenty of ways to handle models like this, too, and they're very closely related to what you guys are going to study. So the good thing is, if I teach you linear regression, you can probably do just about anything else. Like this would be no problem.
Can you say that word again?
Which one? Parabola? Yeah. We're not going to need it for this class, but it is a nice word to know. Parabola. That's the shape of that picture. Okay. Yeah, requirements. Let's see. Simple random sample. We've had that before. Oh, yeah. Number 2 says, make sure you have a line. Guys, you should look at a graph of the data before you start messing around with correlation coefficients. Why? Because if it's like this, you can do a lot of work for nothing. Right? Number 3. There it is. The outliers must be removed if they are known to be errors. And then, so outliers can really mess around with R. Do you guys remember what an outlier is? Remember my Michael Jordan example for the salaries? Something, it's just way out of line, literally. You're going to see outliers in this chapter sometimes. And that happens, and then you have to ask yourself, well, maybe there was a mistake made with the data. And so we have to be careful about outliers. Okay. Oh, yeah. Here's a whole bunch of symbols that you need if you really want to compute R by hand. Yeah, I don't want to either. Look at all those symbols. Those are beautiful. Oh, this is kind of interesting. I guess I will share with you the bottom symbol there. That's not a P, although it looks like it. That's a Greek letter. That's the Greek letter rho, which is the Greek R. So R is a statistic. Rho is a, what's the word? A parameter, because it goes with the population. Okay, so rho is what R estimates. Yeah, here's the crazy formula for R. I'm not going to go there. I think it's time to go to linear regression. And then we'll come back. Well, not quite yet. Let's get to a problem where we compute R. Use calculator or computer if possible. Yes. So they said some of this stuff. Here we go. Here's the problem we're going to try.
So you
Oh, I do want to do that one. Yes, I do. But let's do this one first. Then we'll come back to that. So actually, what I think I'm going to do is I'm going to throw this data onto an Excel page with you. And then we'll try and do some computing here. Okay? And by the way, I guess what we have, what is it that they're measuring here?
Can you make it a little bigger?
Yeah, let's make it bigger. Tell you what, we'll do the computing in Excel in a moment. Let's just see how it all works first, and then we'll try and follow. Okay? So, cost of a slice of pizza, Subway fare. Do you guys know what CPI stands for? I think it's Consumer Price Index. Okay? Anyways, I'm going to stay away from the CPI. I'm going to analyze the cost of pizza and Subway fare. Actually, I'm going to pause for a second. I'm going to let you guys look at the cost of pizza and Subway fare. And I guess my question is there a correlation? And if so, why? Can you guys talk about that data set with your group for a minute, and then we'll come back. If you are to put this into, say, Excel, and we'll do that in a moment, I think, you could plot the data, right? And it says using software or calculator, R will automatically be calculated. And so rather than go through the whole formula in depth with you guys, we're just going to learn how to compute it and then interpret it. So looking at the data here, is there a linear relationship? Well, yeah. I mean, it's almost a straight line through those points, right? There were 2 years that I think it didn't match exactly. And so it looks like someone was using Minitab when they did this. Look at the correlation coefficient. 0.988, okay? I want you to understand that when the correlation coefficient is close to 0, there's no relationship. But if it's close to either 1 or -1, that's when you have a relationship. Is that close to 1? I guess the real question is it close enough to 1? How close does it have to be, Paul? Because you showed us 80%, you showed us 90%. Well, we're going to handle that question like we've done before. So it says we can base our interpretation and conclusion on a p-value. Or, what's the other way you can think about hypothesis testing? Either p-value or critical value, right? And so it turns out that this is kind of the picture. Now, it says critical values from table A6. So where's that? Here, let me show you. In the, oh, thanks for signing me out. I appreciate that. On these tables that come with the book, you have all kinds of tables, right? But there's one, table A6, where they give you critical values, and that's right here on the side of this particular one. I'm going to zoom in so you can see a little bit, and then we'll zoom back out. Okay, there's table A6. Critical values. And if I zoom in a little more, you can probably see what it says. It talks about N, and there's a column for alpha being 0.05. What's alpha stand for again?
Significance level.
Yeah, the significance level. Oh, that's really not working. There we go. Alpha's 0.05 or alpha's 0.01, right? And so depending on N, they can give you a critical value, right? What was our N? How many data points do we have for the pizza problem? 6 pairs. Okay. So if you look, N is 6, they'll tell you, hey, your critical value is either 0.811 or 0.917, right? Actually, I don't care which one we use, because what was our test statistic? We got R was 0.988, right? So I guess the point is, whoa. In this particular problem, we are past the critical value, right? Even if you use the 1% significance level, you're past the critical value. And so what do we say? We say there is a correlation. It's funny. This really mirrors what you guys were just doing. The null hypothesis is that there's no correlation. The alternative hypothesis, which is when we reject the null, which is what we're going to do here, is that there is a correlation. So that's kind of interesting. But on the other hand, if you just understand that, hey, when R is really big or really small, that's when we have a relationship. We can say that there's a relationship. Now, I want to jump to the other slide here. I think that's actually a good idea. Because in addition to asking, is there a relationship, we want to ask, well, what is the relationship? And it's called a regression line or a regression equation. And we can use the software to not only plot the points, but it can plot the line that goes through those points. So I guess I'd like to show you how to do that. I'm going to skip ahead to the example again. But again, the regression line fits the sample points best. That's what we're going to say. Of all the possible lines I could draw through the data, there's a line that will go through that data the best. And so I guess I'd like to show you how to do it on Excel, since you guys are going to be using that for your project, many of you. You could do it on StatDisk. You could try that. But let's go ahead and use Excel, get that fired up, and go from there. Okay, so I have Microsoft Excel here, and I just have to type in my data. So let's see. I have 0.15 for 15 cents, right? And then I have 0.35. Maybe I'll make this a little bigger for you guys. Right? So this is the price of the pizza. Maybe what I'll do, I'll just move this down a little bit. And I'll label it so we're a little more careful here. Here's pizza, and here's Subway. And I don't mean sub sandwich. I see pizza and Subway next to each other. All right, so let's see. 0.15, 0.35, $1, 125, 175, and $2. So that's the price of a slice of pizza throughout the years. You know, you could, I suppose, move this over. We could have a column for what year it is too, right? 1960. Oh, how'd I move it? If you highlight it all like this, Sierra, well, you could do it that way. That's a good way to do it. What I did was this. I kind of put my cursor on the border until I got this symbol, like right on the, not on the corner, but on the side somewhere, and then you can kind of move it where you want. But yeah, copy and paste would work well as well, or cut and paste. Oh wait, that was not 1980. This was 1973. And this was 1986. 1995. 2002. And 2003. Okay, now let me put the Subway fare. So it was also 15 cents back in 1960. In 73, it had risen up to 35 cents, just like a slice of pizza. And then it cost $1 in 1986. And it cost $1.35 to ride the Subway in 95. $1.50 to ride the Subway in 2002. $2 to ride the subway in 2003. I guess to ride the Rapid here in Cleveland nowadays, well, it's $2.50 if you have no discounts, I guess. So $2.50 would be a one-way trip. We might ask, does that match up with this data? It's interesting. It's a different city, of course. Okay, so question is there a relationship between pizza fare and subway fare? And so I'm going to go to Excel Stat. And so let me launch that for you. Mine's not on yet, so I have to press this button to get it going. And so what you want to do, guys, is you want to find, there's a whole menu, I guess, for linear regression if you have the full version. Now, if you're like me and you just have the free version at this point, they still give you this linear regression right here. So this is what I'm about to press, linear regression. If you have the full version, let's see, where is that? It's under modeling data. So if you can't find this, look for something that says modeling data, and you ought to get linear regression. Okay? And we'll press that here in a minute. So let's go ahead and do it. Linear regression. We're going to press that button. Okay, so it's going to get ready for linear regression. And it's going to ask me again, where's the data, right? And there, again, there's a few options here, so we have to be careful. It says Y dependent variables, and it also says X. So you have to keep track of which one's which. The way I decided to do this, right, was I was going to let Y be the subway. But let's see, just so we can kind of match up with what they did. Here, let me compare to their picture. Here, when they did this problem, where's their graph of this stuff? Yeah, they're having the X coordinate is pizza and the Y coordinate is subway. So if I want to make it look like them, I'll make the Y be subway. If you do it the other way, guys, that's fine. It's just your graph will look different. But your results should be the same. Your final results should be the same. Your equation may be different. Your graph may be different. But any questions you want to answer should work out the same. Okay, but just so we're all the same, let's make Y be subway. And so I'm going to, where this is quantitative Y dependent variable, I'm going to highlight this data here. And so it says for me that it's, from C2 to C7. I'm not sure which yours is, because everyone's a little different. But I highlighted the Y values there. Now here, it says, do we have quantitative data? Yeah, we want to leave that check marked. And in this box, I'm going to hit what the X variables are. That's pizza. And so I'm going to go ahead and go from here to here. Okay. So that's pizza as well. We're going to put the output on a new sheet. Oh, guys, one thing you have to check. See, this says variable labels. Only check that if you highlighted pizza and Subway. Otherwise, this should not be checkmarked. So I think that's it.
I'm sorry.
I don't have either of these things checkmarked here, right? And I don't want them to be. Yeah, I don't want to checkmark those things. So I think we're ready. We'll just click OK and see what happens here. Right? Okay. It's going to ask you, hey guys, is it true that you have 6 rows? And the answer is yes, I do. So I'll continue. And so it's going to generate a whole bunch of data on a new worksheet, linear regression. Okay? There's a lot of stuff going on here. What I'm going to point out, and let me zoom in so you can see a little better. Okay, summary statistics. Here, the correlation matrix. Guys, this is the piece of data I'm interested in here. It says 0.988. That's my correlation coefficient. Right? So, also, if we go down a little bit more, so here's some, there's a whole bunch of statistics we're not going to get into. Here, when they talk about analysis of variance, and we're going to be talking about analysis of variance in a little bit. But where it says, someone's printing, the p-value, okay? You can find the p-value right here, probability bigger than f. So the p-value is basically 0. And down here we have an equation of the model. So, boy, is that ugly the way that comes out. But I think if you take this equation and if you round it when we write it down, then we're okay. All right? So what does it say? It says y1 equals 0.3456. It's huge. And then it has the e. Do you guys see that e? Negative 0.02. Do you guys see that? So what does that mean? That means it's a really small number, right? I mean, basically, what I have, okay, if I can read that carefully and write it down carefully, I have y equals 0.0, it says e negative 2, right? 345. So 0.035, I'll say, because I'll round, plus what? And then after the plus sign, do you guys see the plus sign? It's kind of all mushed together. Plus what? It says 0.945 times x1. And so I'm going to say plus 0.945x. This is my linear regression equation. And so if I were to use that equation, I can now compare, that expresses the relationship, say, between the slice of pizza, the price of a slice of pizza, and the cost of taking the subway. You guys with me? Okay. There's more that it gives me. And again, we're only going to cover somewhat. Oh, you guys know what this is? There's some review from a while ago. Remember a box plot? Okay. But here's the picture I want to show. Regression of y1 by x1. R is 0.976, right? So that's my R value. And it shows the data, and it shows the best fit line right in the middle. So that solid line right in the middle is the graph of y equals 0.035 plus 0.945. Okay, so the model, y1, would be this. That line is the best line through the data we could do. And there's a lot more here. But again, this is kind of beyond. We're not going to do residuals in this class. Okay, so how do we use this information, right? Well, suppose I ask you guys, hey, based on the data, can you tell me what you think the price was so, for example, At some point, the Subway fare was probably 75 cents. What do I think the slice of the cost of pizza was at that time? So here's a problem. Problem. When the cost of pizza was 75 cents, what was the cost of Subway fare? Well, what would you say? Well, first thing you might say is, for this example, you might say, oh, it's about 75 cents, right? Because they've been about the same every time. But if we wanted a better value, what's the best answer I could give to this problem? Now we have it based on our model. But we have to remember what's what, right? So up at the top, I wrote down what X and Y stood for, right? Oh, no, I didn't. I said X was shoe print and Y was height, because that's the other problem. All right, what's X and Y for our problem here? Well, I did say it, I just didn't write it down. Here, let's say it again. Here, X is, that was the Subway fare or the pizza fare? I'm going to double check. I have X as the cost of pizza, right? Because my picture, where's the graph? Yeah, X is the cost of a slice of pizza. It's important that I keep track of which is which, right? So X is the cost of pizza. Y is the Subway fare. Let's keep that straight. All right, now I'm ready to answer the question. When the cost of the pizza was 75 cents, what was the cost of a Subway fare? So that says the 75 cents should go in where? X, right? And so we'll do the computation. So we have Y equals 0.035 plus 0.945 times 0.75. And all I have to do is just take my calculator out, work that out, and I'll give you the cost of the Subway fare. So let's do it. Calculator? Yeah, why not? So let's see. 0.035 plus 0.945 times 0.75. Oh, okay. So, what do we get from our model, guys? Well, what was the Subway fare going to be? I guess it says 0.74375, right? But I'll be honest with you, there's no way that a Subway would charge 74 cents, right? Because they don't want all the pennies. So if you said to me, that indicates 75 cents, I'd say, yeah, you're right. Okay. So maybe this is not the best example we've ever had. But I think it demonstrates kind of what you're going to be doing in terms of homework, right? If there's a relationship, then we can use the model. Now, if not, then what do we do? That's a good question. All right? So we're going to do problem 16 in section 10.3. And by the way, the homework's kind of matched up. Some of these problems from section 3 are the same as the ones in section 2. Okay? So it says, at 6,327 feet, the author recorded the temperature. Wow, so Triola has a plane or what? I don't know. So he made some recordings here. Altitude and temperature. Find the best predicted temperature at that altitude. How does the result compare to the actual recorded value of 48 degrees? I guess what I don't understand here is what are the units? Well, I don't know. 3, 10, etc.
Altitude would be feet and temperature would be probably Fahrenheit.
Yeah, temperature would be degrees Fahrenheit.
Altitude.
But that's weird, like 3 feet? What are they
Oh,
saying there?
I think it's maybe it's 1,000 feet. I'm looking at the first one.
Yeah, it probably is.
1,000 feet
Probably is 1,000 feet. Yeah.
makes more sense.
3,000 feet, it's 57 degrees.
Yeah, so it's really
Oh, right. And then 10,000 feet, it's 37 degrees.
okay.
So, yeah, that's what these are. Thousands of feet. Okay, thanks, Sarah. So, when we look at 16, maybe the first thing I have to do is figure out what are we going to use for which variable, right? And so I'm going to let x be the the altitude in thousands of feet. All right? So here I go. Let's remember, let's start out by writing that because we're going to need that information, right? So problem 16, and this is section 10.3. Let's let x be the altitude in thousands of feet. Let's let y be the temperature in degrees Fahrenheit. Okay, I like that. And now, what I'm going to do is, since Sarah asked about the calculator, let's put the data into the calculator this time, right? So they give me these data points here. And what I'm going to do is I'm going to start putting those into our calculator. All right. So to put things in the calculator, I hit the Stat button, right? I'm going to edit my lists. And I'm going to use two lists here, L1 and L2. But I kind of need to clear them out first. So I'm going to show you, remember, don't hit delete when you have your cursor on L1. You want to hit enter. When you get down here, you can clear everything out by hitting the clear button or the delete button. And then press enter. If you go on top of it and press clear, it'll just remove the list. So I press enter when I'm on top of L2. Then I press clear. And then another enter gets me 2 blank lists. Remember, Jawan, you were asking me about this on Friday. It's what it is, right? So once I have cleared lists, I can put these things in the calculator. Do you guys want to do this along with me? It won't take that long. Let's see. So we have, 3, 10, 14. So that's 14,000 feet, right? 22,000 feet. 28,000 feet. 31,000 feet. And 33,000 feet. Okay. And now we have some temperatures. So this is a spring day, 57 degrees, right? Oh, but that's at 3,000 feet high. Well, maybe that's, how many feet above sea level is Cleveland? Kirtland. I don't know. Might be 1,000. So anyways, when you get up to 10,000 feet, it says that the temperature is only 37 degrees there. Right? At 14,000 feet, we're at 24 degrees. By the time you get up to 22,000 feet, now we're at negative, right? So negative 5 degrees Fahrenheit. Uh-oh. Go to my error. I bet you I have the wrong negative sign. I certainly do. Got to press this negative sign for a negative. Okay. At 28,000 feet, I have negative 30 degrees. At 31,000 feet, we're at negative 41 degrees. That's cold. And then at 33,000 feet, I'm at negative 54 degrees. You guys with me? So when you're all done here, yeah, second quit is the way to get out of the lists. So I'll hit second, and I'll hit quit. Okay? And now I'll hit the stat button. The stat button, and this is what Sarah asked me, are you going to use linear regression t-test? Let me show you where that is. If you go to tests, now, it's funny, we've done a lot of these tests this year. This one is so far down the list that you can actually get there more quickly if you go up. So I'm going to hit the up arrow. And now I'm at the end of the list almost. Well, ANOVA is the end. There it is. Linear regression t-interval. Nope. Linear regression t-test. That's what I'm going to use. And it says this in the book. I'll go ahead and press enter. And all it asks me is, where's your data? The X's are in list 1 and the Y's are in list 2. That's good. Oh, one more thing. This is kind of interesting. They ask you, hey, what about rho? Do you want it? So you know what I'm looking at here is that rho, this is a hypothesis test. And maybe tomorrow I could show you a little more how that works. Or maybe at the end of class today. We'll see. Okay? It shouldn't really matter for our purposes. I'm going to click on the not equal to, and I'm going to click on calculate. Okay? So what we have here is we have, notice it says y equals a plus bx, right? So what would be the regression equation? Well, what you have to do is you have to plug in a and b, right? The calculator says y equals a plus bx, but you need to plug in a. A is 72, right? So what does that say? I would write y equals 72, right, plus bx. So b here is what? Yeah, negative 3.7, right? So I'll say minus 3.7x. Oh, and one other thing you better check. Is this a good correlation or not? Remember, this is a Section 3 problem. But Section 2 says, does a correlation exist? Well, we have to check that first. Let's see. What's my p-value? P-value is really low, really close to 0. That means there's a strong correlation, all right? Matter of fact, if I hit the down arrow here, I think they'll give you the value of R. Let's see if they do.
Negative 0.99.
Yeah, so that's really close to what?
Negative 1.
To negative 1. Yeah, right?
So how do you know if it's a strong correlation again?
So again, if I go back to the correlation slide, I think this kind of shows it. That's 10.3. Let's go to the correlation slides here. 10.2. It really comes down to this idea. If you have a low p-value, right, or if you're past the critical value in the critical region somewhere, then you have a correlation. So where am I on this picture this time? I'm way to the left, almost to negative 1. I'm in the critical region.
So was it always going to be 0.8 or 1?
This critical value corresponds to a 5%. No, it's not. Let's say no, it's not. And that's why, honestly, I think you're better off looking at the p-value. So what was my p-value on the calculator?
0.003.
Yeah, that's way below 5%. Wait a
So
minute.
we're still doing like the p greater or less than
Yep.
alpha?
Yep.
What's-
This p-value is really low, way before 5% or 1%.
Which alpha do we use though? Do I always use 0.05?
I think I would use 5% unless it says otherwise, but they'll typically make these really extreme examples. Okay,
So when it's low, then there is a strong correlation.
that's right. The null hypothesis is that there's no correlation. The null hypothesis is that there's no correlation. Okay, so here it's kind of funny because what I would say next is when I'm thinking about this problem, right? Because the question asks, find the best predicted temperature at that altitude. Okay, well, here's what I would say. Because R is close to -1, the linear model, the linear regression equation, I got to zoom out just a little bit here. Is a good model. So I will use it to answer the question. But there are times when you can't use the equation. If you have a linear, like if you got R as 0, you wouldn't want to use the data. You wouldn't want to use the equation. But anyways, how do I use it to answer the question? What did they ask? They asked
What would it be if it was 48 degrees Fahrenheit?
48 degrees. Degrees Fahrenheit, oh, wait a minute. I'm putting that in for Y, right? So sometimes you have to put the value in for Y rather than X. So I would put my 48 here. 48 equals 72 minus 3.7x. And if I just finish up here, I have to do a little bit of algebra at this point, right? So I get negative 24 is equal to negative 3.7x, and I'll divide by negative 3.7 on both sides. And I'll get x. So I guess I have to do 24 divided by 3.7. Let's see. Something seems wrong here. Well, we're past time, guys. I will fix this up next time.
Is it 6.649?
I made a mistake, and we're over time. I'm going to pause and come back to